All right, let's just jump right in. For pretty much all of human history, we've looked at our vast oceans and thought, yep, that's where all the water is. But what if I told you that was completely wrong? What if the biggest reservoir of water on Earth isn't on the surface at all, but is actually buried deep inside the planet and, get this, it's the very thing that makes our world tick? So let me ask you a question. If you had to guess, where is Earth's single largest stash of water? You're probably thinking the Pacific Ocean, right? I mean, it's huge, it makes sense. But some really incredible science is telling us we need to look way, way deeper than that.
And the answer is just, well, it's mind-blowing. Deep inside the Earth's mantle, scientists now think there's enough water to fill our surface oceans 3 times over. Just let that sink in for a second. 3 whole oceans worth of water, completely hidden from sight.
Okay, now hold on. Before you start picturing these massive underground caves and giant liquid seas, that's not what we're talking about. It's not an ocean in the way we think of one. It's something way weirder, and honestly, a lot more interesting.
This colossal water reserve is locked up in a really specific part of the planet called the Mantle Transition Zone. We're talking hundreds of kilometers straight down, a place with pressures and temperatures that are almost impossible to imagine. And this is where the real story starts.
So that leads to the obvious question, right? How in the world can solid rock hold an ocean, let alone 3 of them? Well, the secret isn't in a big empty space. It's actually inside the atoms of a very special kind of mineral. Everybody meet ringwoodite. This stuff is amazing. The best way to think of it is like a crystal sponge. Under the insane crushing pressure of the transition zone, its molecular structure literally has little spaces in it that can grab and hold on to water molecules. It doesn't get wet, the water becomes part of the crystal itself. So obviously we can't just send a drill down 600 kilometers to check this out. So how do scientists even know any of this? Well, they have to get really clever. They basically have to build a tiny version of the Earth's interior in their labs and another one inside a supercomputer.
And this is so cool. You can see their 2-pronged strategy right here. On the left, that's the real-world experiment, a machine that uses multiple anvils to create the kind of pressures you need to actually form ringwoodite. And on the right, that's the virtual Earth, a computer simulation where they can watch how the mantle behaves over millions and millions of years.
Let's just quickly break down how they do it. First, in the lab, they make these tiny little crystals under all that pressure. Then, they measure everything about those crystals, how they conduct heat, how strong they are, you name it. Then, they plug all that real-world data into their supercomputer models to see how a planet made of this stuff would actually behave.
And it was through this exact process, combining the real and the virtual, that they stumbled onto something huge. A totally unexpected discovery about what that trapped water actually does to the rock it's in.
And here it is, the big reveal. When you look at dry ringwoodite versus ringwoodite with water locked inside it, what they call hydrous ringwoodite, you see this massive difference in one key property, how well it lets heat pass through it. The dry stuff is a decent conductor, but the wet stuff, it's a terrible conductor. It traps heat.
I mean, look at that number. It's wild. You add less than 2% of water by weight to this mineral, and its ability to conduct heat drops by almost half, a 44% reduction. That's a ridiculously powerful effect from what seems like a tiny amount of water. Really, the easiest way to picture it is just like this. The water acts like a thermal blanket. The wet rock deep inside the Earth is an incredible insulator. It just holds on to heat and refuses to let it escape. And that simple fact changes, well, it changes everything. But, okay, who cares about a thermal blanket hundreds of kilometers down? Why does that matter to us up here? Because it turns out it has a direct effect on the most important geological process on our planet, plate tectonics. So to get this, you gotta follow the life of a tectonic plate. It gets born at a mid-ocean ridge, it cruises across the ocean floor for millions of years, and then, eventually, it gets old and heavy, and it sinks back down into the mantle. That's called subduction. But the big question has always been, what happens when it gets down to that waterlogged transition zone? And this is where it all clicks into place. Because of that thermal blanket effect, the wet parts of that sinking plate stay colder for much longer than the dry parts. And since colder rock is denser rock, it changes how it falls. Instead of just punching straight through to the lower mantle, it's more likely to get stuck, to just lay down flat and stagnate in the transition zone. And when it does that, it releases all its water, feeding that massive underground reservoir. It's a self-sustaining deep water cycle.
And this isn't some minor geological detail. The researchers themselves say that this deep water cycle might be the key element that allowed plate tectonics to even start on Earth in the first place. Without this hidden ocean, our dynamic, churning planet might look totally different.
And you want to know how different? Just look next door at our sister planet, Venus. Venus is bone dry. It has no deep water cycle. And guess what else it has? No plate tectonics. Its surface is just one solid, static, hellish lid. This comparison shows you what's at stake. That hidden water might be the very thing that keeps our planet geologically alive and ultimately habitable.
So that leaves us with this incredible, profound question when we look up at the stars for other planets like ours. It's not enough to just look for water on the surface anymore. The real question might be, does that planet have a hidden ocean deep inside? Does it have the secret engine that's needed to bring a world to life?